Okay, so what we were just saying was that when you swing anything in a circle, like a bucket, if you swing a bucket in a vertical circle around your, beside you, the water will go to the outside edge as you swing around. The same is true for any liquid. So when we swing you around in a circle, the liquid in you will go to the outside edge. So when you're inside a loop, the blood in you goes to your feet. And your heart has to work really hard, pump really hard to get enough blood and therefore enough oxygen to your head so that you don't black out. If the speed is too fast, then it's too much for your heart. So for a regular, typical, stereotypical person, and none of us are, but in standard uniform shape, no heart conditions, so people who have medical issues would be able to withstand less. People who are in really good shape and have done training would be able to withstand more. But the limit is usually 8 Gs. So if over 8 Gs, the regular person's heart is not able to pump fast enough to get enough blood to our brain to keep enough oxygen to our brain. And at 8 Gs is known as the blackout limit, because at that point, we will black out from lack of oxygen. Now, if we black out from lack of oxygen, we pass out for just a few seconds. It's no big deal. If it's too long, we can get brain damage. But if we just hit it and pass out and then come back to, and sometimes it happens to some of us if we stand up too quick, and then the whole room goes black, and it's because your heart isn't able to get enough blood to your brain quick enough. And that doesn't result in brain damage, but obviously if we're in a situation where this lasts for too long, it would. And so when we're designing rides where your head is inside the loop, we have to make sure that we don't exceed 8 Gs. The other one is outside the loop. So this is when you're going around the outside of a loop. So here's my loop. Here's the chair, and here I am. So if you think about loops in a roller coaster, most often our head is on the inside. This would be like a Ferris wheel or something like this, where we're going, or over the top of a hill in a roller coaster. Okay? Now, the same thing is true when you're outside the loop. The liquid still goes to the outer edge, and when you're outside a loop, the outer edge is your head. So now all the blood is going to your brain as you go around here. And so your heart has to work really, 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 really hard to keep too much blood from going to your brain. And the problem is when too much blood goes to your brain, then it can pop all those little capillaries that are in your brain. And when it does that, there's no unpopping them when we slow you down. So this one's much more dangerous because those little capillaries in your brain are a lot more fragile than, and can't be unpopped. So the limit here is 3 Gs. And this limit is called the readout limit. And that would be because if those capillaries pop, there'd be a lot of red. Okay? So that's why you would not be going around the outside of a loop on a roller coaster loop. You'd be going around the inside because you could go much faster without the same kind of danger. You can also run into an issue with G's when there's a linear acceleration, right? Because these are centripetal accelerations. But in a linear acceleration, maybe you're in a cart on a ride, or maybe you're in a car on the road, and you're going in a straight line. If you exceed 20 Gs, then bleeding from your ears will occur. And at 40 Gs will be death. Even if you're strapped in, even if you have your seatbelt on. And that's because the seatbelt will stop your exoskeleton, but the organs in your body will still have to slow down. And at 40 Gs, even though the space isn't very big in there, those organs will rip off. Okay, so we don't want to exceed 40 Gs in a car crash or on a ride. Now, how do we figure out the number of Gs felt? Number of Gs felt is what we said is important. And so the definition for the number of Gs felt is the normal force, and you should write this down, the normal force on the seat of the rider, on the seat of the rider, divided by the mass, and then converted into Gs. And of course, to convert into Gs, it means divide by 9.81 meters per second squared. Okay? So let's think about when we're going around a loop. We'll get our, we'll figure out our equations for at the bottom of the loop and at the top. So I'm going to show you how to derive them. You'll never have to know this. I just want to show you so that you'll know where these equations come from. So we're at the bottom of a loop with our head inside. Fg will be acting down. Fn will be acting up. And so we want to figure out the normal force to get the number of G's felt. So we're going to do Fc is equal to mv squared over r. And towards the center is positive. So Fn minus Fg is equal to mv squared over r. So our normal force will be equal to mv squared over r plus mg. So now our definition is the normal force of the seat on the rider, got it, divided by the mass. So when we divide by the mass on this side, the m's cancel out. So we're left with v squared over r plus g. Well, v squared over r is really just AC. It's an n over m. So this is really AC plus g. And it says divided by the mass and then converted into G's by dividing by G. So now we have to divide both sides by G. And so when we do, this becomes our number of G's felt, because that's its definition. And that's going to be equal to AC over G, and G over G is plus 1. So at the bottom of a loop, the number of G's felt is your centripetal acceleration divided by G plus 1 at the top. So here I am at the top of the loop. Okay, and remember, my head's still hanging in. Okay, so Fg is going to be acting down, and so is Fn. So when I do sum of the forces is equal to mv squared over r, it's going to be Fn plus Fg. Remember, towards the center is always positive. I'm still trying to find my Fn, so I take my Fg over. So mv squared over r minus mg this time. And so I have the normal force. Now I have to divide both sides by the mass, because that's what it says in my definition. And again, my m's are going to cancel. And the v squared over r is going to be AC, so AC minus G, and then convert into G's by dividing by 9.81. So divide this by 9.81, or little g. So this becomes my number of G's felt, because that's the definition, will be equal to AC over G minus 1. So when you're at the top of the loop, to get our number of G's felt, find the centripetal acceleration on the rider, divide it by 9.81, and then take away 1. Take away 1 because Fg is helping here, so Fn isn't going to be as big because Fg is acting in the same direction, so that's why there's a minus. Add 1 over here because Fg is working against the Fn, so Fn has to be bigger. Not only does it have to supply all the centripetal acceleration, it also has to balance out the Fg, okay? So at the bottom, at the top. So your questions tonight on the roller coaster, you'll need this at different spots. All right? Very good.